Okay, so this is a video that is concerned with the proof of asymptotic efficiency of a GMM estimator using an efficient weighting scheme, which we discussed in the lecture. So I already wrote some results that we've had earlier, in particular the asymptotic variance-covariance matrix of any GMM estimator in this generic form that we see here. And it turns out if I use this efficient weighting scheme, as we've discussed in the lecture, so I use for A, d prime s to the minus 1, and I plug this in the general formula, I get an asymptotic variance-covariance matrix expression that looks like that. So I slightly changed the notation a bit. There's an estimate that results from the weighting scheme A, and there's an estimate that results from the weighting scheme using s to the minus 1. Okay. Now let us denote these two asymptotic variance-covariance matrices in an even shorter way. So I like to denote this asymptotic variance-covariance matrix as V of A, and this asymptotic variance-covariance matrix I like to denote by V of s to the minus 1. Okay. Now, as discussed in the lecture, and I provided the intuition there, what we need to show is that the difference of the two asymptotic variance-covariance matrices is positive semi-definite. Right? The intuition behind that claim is given in the lecture, so please recall the stuff that we've discussed in the lecture, please. Okay. So, in order to show the positive definiteness of the matrix difference, what we need to show, what is useful is to consider the sampling error. Okay. So I'm considering the sampling error of the GMM estimate using the weighting scheme A, and we know that we have a limiting distribution of the sampling error, which reads as follows. Okay, where this random variable x, this thing actually is where square root of t, gt of b converges to in distribution. We know that the distribution of that random vector is the normal distribution with mean 0 and variance-covariance matrix given by S. Okay, where then we have when the convergence in distribution then of this term on the right hand side is then by the Slutsky theorem, or by the property of the normal distribution actually, is the normal distribution with a with mean 0 and a variance-covariance matrix that is given by the following term. Now again, in order to keep the notation a bit briefer, I like to denote this term, right, which I underbrace as M of A. Okay, so that's M of A from now on, and the distribution then is M of A times S times M of A prime. Okay, and that is, as a matter of factly, that's what we denoted up there as V of A. Now, let's consider the efficient weighting scheme and the sampling error that is implied by it. Okay, here's the sampling error. And we know that the sampling error converges in distribution then to the following term, plugging in d prime s to the minus 1 for A. the general formula, we get this result, and I like to call this term over there m of s to the minus 1. Okay, a non-random matrix. The distribution of the term is then again the normal with mean 0 and a variance covariance matrix that we can denote like this. And we call this object above v of s to the minus 1. So these are the sampling error expressions of which we know a convergence in distribution. Now, what is helpful for the proof is to apply an add and subtract strategy. So I'm going to take the sampling error from here, have it on the left-hand side, and have it again on the right-hand side. So I'm taking this guy again and put it on the right-hand side of the equation. What I'm then do is I'm adding and subtracting the sampling error obtained by using the efficient weighting scheme. So it goes here, and I want to have it again. Here. So in order to have a proper equation, I have the sampling error using the general weighting scheme here. I'm going to add and then subtract the sampling error of the efficient weighting scheme. Okay, let's take a look at what happens in distribution with left and right hand side. So we have a convergence for that term to m of a times x, which we have there, and this thing is distributed normal with mean 0 and what we call the variance covariance matrix V of a. Okay. Recall that this is MA S MA prime. Okay. As denoted above. Now, about this term, we have a convergence in distribution to distribution of this line variable. Okay, we denoted this term as we can denote. Let us denote this term m of s to the minus 1 to again abbreviate the notation even further. Let us denote this thing by a. And what about the remainder on the right-hand side? Now I like to summarize the two terms and say, okay, this term is going to converge in distribution to a random vector, and this random vector looks as follows. Okay, and I like to call the term in brackets B. Okay, so if we take a look at the whole right-hand side of the equation, what we're going to see is that we have a convergence in distribution that we can write as follows. So this thing converges in distribution to a normal distribution with the mean 0 and a variance covariance matrix that is given as follows. So a plus b s a plus b prime. Okay, and that is then because both sides are identical, the term that we see on the right hand side here, that's sort of what we could call the variance covariance matrix that we call the V of A, right? And this is what is exploited now in the next step. Okay, so I'm going to use this result and write the variance covariance matrix VA as follows: say plus B multiplied with S, and then I'm basically solving the parentheses and saying, okay, this is multiplied with A prime plus B prime. Okay. Now what we can do is we can use the usual laws for working with matrices. Commutative and distributive laws hold, so we can write the right hand side as follows. We have A as A prime, we have B as B prime, we have B as A prime, and we have A as B prime. Okay. Now let's take a look at the terms on the right hand side. We recognize that this is what we refer to as the variance covariance matrix, which is obtained using this optimal weighting scheme. This term didn't have a name yet. I like to call it V1. This term also doesn't have a name yet, so I like to call it C. And we recognize that the term here is the transpose of C. So that's C prime. Now we're talking about a matrix difference, so let me bring a V of S to the minus 1 to the left hand side. Okay. So we have then on the right hand side V1 plus C prime. Now remember, our job is to show that the left hand side is a positive semi-definite matrix. To verify that, we take a look at the terms on the right hand side. And first I'm going to focus on V1, right, and on this term. And I argue that V1 is actually a positive semi-definite matrix. Okay. So V1, which is equal to B as B prime, that's a positive semi-definite matrix. And to see that this actually is true, we can take a bit of a look at the components of V1. So what we observe is that S is a variance covariance matrix, right? Of X, as a matter of factly. So that it would be an n by n matrix. So it's a square matrix, it's a symmetric matrix, and the matrix is also positive definite. Okay. Now, what is a characterization of a positive definite matrix? It means that the eigenvalues of this matrix are only positive. Right? This matrix is a full rank, the variance covariance matrix S, though there are no zero eigenvalues. All eigenvalues of the matrix are actually positive. Now what we can do is we can say, okay, if this is true, S is a symmetric and square matrix, so we can basically apply the spectral decomposition that we've encountered earlier, and also exploit the fact that the eigenvalues are all positive. So we're going to write S as follows. We write S as C prime. So essentially this is a spectral decomposition recognizing that all the eigenvalues are greater than 0. Okay. Now recall what a spectral decomposition looks like. We have essentially S, which is let me call this thing C tilde, lambda C tilde prime. And what I could do with this decomposition with positive eigenvalues, I could basically say, okay, this is C tilde and the square root of lambda multiplied with the square root of lambda and have C tilde prime here. Okay. Now what is lambda to the 1/2, the square root of lambda? Well, that is a matrix that takes the square root of the eigenvalues of S on the main diagonal, and there are zeros off. Remember that lambda is a diagonal matrix which contains the eigenvalues on its main diagonal. Okay, and the square root of that matrix is basically looking like that. It's a matrix that has on the diagonal the square root of the eigenvalues. And you see, this is important. These eigenvalues need to be positive. Otherwise, I couldn't do that. I couldn't make this decomposition. So again, let me write S as C tilde lambda 1/2 lambda 1/2 C tilde prime, and then we may define this term as C. This term is then C prime, and we get the desired result. Yes, we can write a symmetric and square and positive definite matrix in this form, so with C and C prime. Okay. And I'm going to exploit this result over there in my proof or my showing that V1 actually is a positive semi-definite matrix. So for that purpose, I'm going to reinsert, or I'm going to insert for S C prime. Okay, and I'm going to use B tilde, and B tilde is just B times C. Now maybe it's worthwhile to remind ourselves a bit about the dimensions of the matrices. B is a K by N matrix, S is N by N, and B prime is N by K. So the variance covariance matrix V1 is a K by K matrix. Okay. B tilde is then a K by N matrix as well. Now, what we can write then is B tilde prime, right? And B tilde prime, I argue, is positive semi-definite. Now, why is that? What we require for this positive semi-definite matrix is that let me write this as because when I write x prime b tilde prime x using any non-zero vector x, what I get is something that is bigger than or equal to 0. Okay, and to see this, we can define a vector y, which is b tilde prime x. You recognize that this is an n by 1 vector y, and using this definition, we get x prime b tilde prime x is the same thing as y prime y, and this is of course nothing more but, well, the sum of from 1 to n of the elements of the vector y to the square. Okay, and this is of course something that is never negative. Okay, remember that y actually is a vector that contains n elements. Okay, and I'm computing the inner product of that vector. Now this shows that V1 is positive semi-definite. It's a positive semi-definite matrix. Now what I also can show is that the terms C, which we have here, okay, these terms actually are zero. Okay, so if you believe me that for the moment, it shows that the matrix difference that we have on the left-hand side is actually a positive semi-definite matrix. Okay. But I need to show that C and C prime therefore are zero. Okay. So let's write this down. We can show that C and therefore C prime is actually zero. And to do that, we're going to start at the definition of C. So recall from above, C is actually B times S A prime. Okay, and I like to reinsert B for what it is and A for what it is to show that C actually is zero. So B is M of A minus M of S to the minus 1 multiplied, which is B. Okay? I multiply this with S, and I have to multiply it with A prime, and that is M of S to the minus 1 prime. Okay. And now we have to further reinsert our terms. So for M of A, for instance, I'm going to insert minus AD to the minus 1A. So that was M of A from above. And I need to subtract M of S to the minus 1. And doing that, I'll have a plus here because M is actually minus D prime S to the minus 1 D to the minus 1 D prime S to the minus 1. Okay, so minus and minus gives you a plus. Okay, so this term would be minus M of S to the minus 1. Okay, I can close the bracket here and have S here, and then we have M of S to the minus 1 primed. So what we get then is S to the minus 1. It's a symmetric matrix, so I don't have to prime it. D S to the minus 1, D prime S to the minus 1 D to the minus 1. Okay, just plugging in the definitions from above. Now what you see is one thing, S multiplied with S to the minus 1 cancels out, or it gives you the identity matrix, and then we can multiply the terms in brackets, and each element of the terms in bracket is multiplied with this term. So what we get is AD to the minus 1. One thing, I've forgotten it, so sorry. Here should be a multiplication with minus 1, right? Sorry, forgot that. So we'll have a minus 1 multiplication in between. So we multiply the minus here with the minus here, and therefore we end up with something positive. Okay, so we have AD to the minus 1, AD, which is multiplied with D prime S to the minus 1D to the minus 1. Okay, that's the first multiplication. And then we multiply this term with this term again. Okay, we have a minus, which gives us d prime s to the minus 1d to the minus 1. Then comes d prime s to the minus 1, which is multiplied with d. And then we have d prime s to the minus 1d to the minus 1. Okay. Now we're going to see that again, a couple of terms cancel out. For instance, ad to the minus 1 goes with ad, so we're left over with this term here. And on the second term, we see that ds to the minus 1d cancelled out with this thing, and we're left with this term, and they're identical, so these guys cancel out and it's 0, and this shows that c is equal to 0, and of course it implies that c prime is also equal to 0. So summing up, what we showed is that when we take a look at the difference of these two asymptotic variance-covariance matrices, okay, we saw that this is the object V1, and V1 was shown to be positive, semi-definite. So this matrix difference is also positive, semi-definite, and this is what we wanted to prove. Okay. So that's the conclusion of the proof of the asymptotic efficiency of GMM. If you use a weighting scheme of that type, you can claim that you provide asymptotic efficiency of your GMM estimates. Okay, so that's the conclusion and the proof. Thank you for listening. If you have comments to these videos, please let me know.